My name is Luqa Ismail-Keyes, and my paper is titled Nonlinear Temperature Effects on Public Transport Demand, Evidence from London. Climate change is expected to increase the frequency of extreme weather events over the coming decades, leading to hotter summers and more temperature variability in the UK. This means that, while mitigation strategies are important, it's also crucial for governments to understand how these changes will affect economic activity in the short term, so that they can invest in adaptation strategies accordingly. While a lot of research in environmental economics focuses on sectors like agriculture, energy, and health, public transport has received less attention. My paper contributes to addressing this gap by focusing on the effect of temperature variability on usage of Transport for London, or TfL, services. I have two main research questions. One, does TfL ridership have a concave relationship with temperature? And two, does that relationship vary across different modes of transport? Results could help TfL to predict changes in demand during extreme temperature events and adjust provision of services accordingly to reduce allocative efficiencies. To answer these questions, I construct a panel dataset using TfL journey counts and weather data. Since TfL reports journeys across 13 recording periods each year, and these periods vary in length, I aggregate them into seasons and calculate average daily journeys so that they could be compared to meteorological records. I also include the share of public holidays in each season and precipitation sum as control variables to reduce omitted variable bias. Methodologically, I estimate a quadratic fixed effects panel regression. I include year fixed effects to control for major year-specific shocks that occur during my sample, especially COVID-19 and the later rise of hybrid work, both of which had substantial effects on public transport usage. After that, I estimate separate regressions by mode and then a pooled interaction model to test whether the temperature response differs significantly across types of transport. My first finding is that there is evidence of a quadratic relationship between temperature and total TfL usage. The coefficient on temperature squared is negative and statistically significant, which implies a concave relationship. In other words, holding all else constant, ridership tends to increase as temperatures move towards a moderate level, but then begins to fall as temperature deviations become more extreme. The estimated turning point is around plus 1.5 degrees Celsius relative to the baseline. The broad conclusion, therefore, is that moderate temperatures are associated with the highest usage, while colder and hotter conditions are associated with lower demand. My second finding is that although mode-specific graphs suggest some visual differences, the pooled interaction model finds no statistically significant differences in temperature sensitivity across buses, the underground, the DLR, and the overground. That means that I cannot reject the idea that these modes respond similarly to temperature changes. In terms of interpretation, my first findings suggest that temperature variability may make public transport demand less predictable. That matters because if demand becomes harder to forecast, transport authorities may face greater difficulty matching service provision to actual passenger needs. One possible explanation is that people have a thermal comfort threshold. When temperatures become too cold or too hot, they may travel less or switch away from public transport. My second finding may suggest that services are used for similar purposes, and therefore the causal pathway from temperature to service demand is similar across the four modes. That said, the paper also has limitations. First, the sample size is relatively small. Second, the analysis uses seasonal aggregation, which may smooth over the short-run effects of extreme weather and reduce the apparent effect of temperature and precipitation. Third, the holiday control does not account for optional holidays, and the analysis assumes temperature is constant across London, even though the city has a clear urban heat island effect. Future research could improve on this by using more temporally precise, station-level passenger data, matched with more spatially precise weather data. Overall, my paper finds evidence that public transport demand in London responds to temperature in a non-linear way, but that this pattern does not significantly differ across the four TfL modes that I study. This suggests that climate variability may have practical implications for transport planning and service provision in cities. Further research should be undertaken to uncover the causal mechanism behind this, so that transport authorities can predict demand accurately during extreme weather events and invest in reducing the temperature sensitivity of urban transport demand. Thank you for listening.